I used to think that computer science was all about coding, but this winter term, I took a computer science class where we didn't write a single line of code. Instead, we wrote proofs and did a lot of math. Caltech calls it decidability and tractability, but it really was just a class about the foundations of computer science theory. So what is that, and why should we care? Just like there's different subfields of computer science, there's many different theories within this discipline of theory of computation, and here are 4 that we'll be touching on later. Essentially, all these theories were developed to answer questions like what can and can't be computed, what is computation, and why is my ass getting kicked in this class? Just kidding about the last one. I will say that knowing theory informs practice, so if you're not interested in theory at all, at least you might become a better programmer from knowing some theory. Anyways, there's problems out there that computers can never solve, and we study the theory of computation to understand what computers can and can't do. In a perfect world, for each problem we would have an algorithm that would be the fastest, and we could prove that no other algorithm would be faster. In our current world, some problems have no algorithms, and for a lot of problems, we know very little about what the fastest algorithm is. Knowing the fundamental capabilities and limits of computers will help us solve problems more efficiently, and we can develop a common vocabulary for which we can use to generate new knowledge. So let's check out some of those theories from before with my friend Emile.
Hi, I'm Emile. I'm a TA for the class you mentioned. Besides studying computer science, I'm doing research to understand randomness better by studying random walks and expander graphs.
Language theory covers how information and computation are expressed, basically asking what is information, and approaches the question with the hypothesis that all human usable information can be represented as a string of symbols.
So yeah, language theory is all about encoding problems as symbols and representations at a level where the computer can understand what's going on and do computations on them. And just to clarify, the languages that we're talking about are computational problems, not spoken languages like English or Spanish.
Automata theory covers abstract machines and automata, as well as the abstract problems that can be solved using them.
You might have heard of Alan Turing, the father of computer science. Anyway, he invented the Turing machine, which is a fundamental model of computation. It's really just a bunch of tapes and heads that perform some calculations to figure out a solution to some input problem.
Computability theory asks, is there a program for every function? The short answer is no, but computability theory is concerned about figuring out which functions are and are not computable.
Yeah, sounds good to me. And to connect it with what we just learned about, function f is said to be computable if and only if there exists a Turing machine that can compute f of x for any input x.
Finally, complexity theory gives us theoretical limits on what can and can't be computed. It tells us what is required to compute a function and finish this question. Answers.
You might have heard of the Millennial Problem. Is P equal to NP? What does this mean? So P is a set of all problems that can be solved efficiently in polynomial time, and NP is a set of all problems that can be verified efficiently in polynomial time. The question of P equals NP asks whether problems that can be solved efficiently can be verified efficiently and vice versa. The 3-colorable problem is that you're given a graph in 3 colors and you get to color each vertex such that for any vertex, it should not have an edge with a vertex of the same color. It's easy to verify that this problem is in polynomial time. All you've got to do is iterate through the vertices and check that for each vertex, you're not connected to a vertex of the same color. And then you've also got to check that the total number of colors using the graph is 3. But what it's not easy to do is to come up with a way to color the graph efficiently when you're just given the graph, and it's actually an open problem.
Okay, so this is related to language theory because our language is 3-colorable, right? And to connect this to automata theory, the Turing machine can verify a solution in non-deterministic polynomial time, meaning 3-colorable is in NP, but we don't know if it's in P.
Right, and we don't know the instructions to give a Turing machine to come up with a solution for 3-colorable, which would actually show that it is in P.
And then to connect to computability theory, we don't know if there exists a Turing machine that can solve 3-colorable, right? So finally, for complexity theory, this is a bit of a simplification, but basically, if you can come up with a polynomial time Turing machine for this, you can basically say P equals NP, kind of like what we talked about.
Yep.
Cool. So yeah, that was a very, very brief introduction to some major theories of computer science, but there's a lot more out there to learn if you're interested or maybe taking a class about the subject. I hope you enjoyed this video and make sure to subscribe so you don't miss the next one. See ya!